To calculate pH of a buffer solution, you need to borrow this equation from your data booklet. It's on page 1 of your data booklet, and it's known as Henderson-Hasselbalch, discovered by the two scientists in order to have a shorthand version of calculation for pH of a buffer. Now this applies to any buffer, and you can have HA to represent a weak acid, and when it donates its hydrogen to a base such as water, it creates an equilibrium because it's weak to give you conjugate base and hydronium ion. So this is conjugate base. Now the combination of the weak acid and conjugate base, this two together, this creates a buffer. And then in order to calculate this pH, I simply need to know pKa of the weak acid, and then concentration of my conjugate base, A minus. So bracket stands for concentration, divided by concentration of the acid, HA. Let's look at a typical problem. Now MES is a buffer that we use in biochemistry quite often. It's a friendly buffer. If you take MES and you add hydrogen to it from hydrochloric acid, the nitrogen gets protonated and you create a conjugate acid. So the combination of this weak base and conjugate acid creates a buffer. So MES, we call it MES in order not to get tangled up with this chemical description. And the protonated version, we call it MES acid. Now the question, for example, is calculate pH of this buffer containing 0.5 mole per decimeter cube, unit of your concentration. So here you have 0.5 mole per decimeter cube. And also you have the same concentration of MES acid. So this is also 0.5 mole per decimeter cube. And pKa of this MES is given to be 6.15 at 25 degrees Celsius. So one of our assumption for using this equation is the buffer is at room temperature, 25. So we say pH equals, we borrow that formula from data booklet, plus log of your base divided by your acid, concentration-wise. So this is equal to 6.15 plus log of, every time that concentrations are exactly the same, your pH becomes pKa, because this ratio is ratio of 1. And you can calculate it or just remember it from now on. Log of 1 is always 0. So this says that pH is equal to pKa, and it's equal to 6.15. As easy as that, you just plug it in. Now the next question is, what happens when we really add a tangible quantity of hydrochloric acid? So in the next problem is, what is the pH of this solution that we just had with pH of 6.15 when 10 centimeter cube of 0.1 molar hydrochloric acid is added to 50 cm cube of this buffer solution? It's easy, but we need to know a little bit of stoic before we go and apply Henderson-Hasselbalch. So what we are going to do is say, look, we have this concentration of MES, and this concentration of MES acid was also there. We have 50 cm cube of this. So if we multiply by the volume, remember 50 cm cube divided by 1000 is 0.05 decimeter cube. So centimeter cube becomes decimeter cube. If we multiply it by this, same thing for MES acid, 0.05 decimeter cube, what we find is moles of the MES initially and moles of MES acid also initially. This happens to be 0.025 moles. If I did my multiplying correctly, 0.025 moles. Now let's see what happens when we add so we are adding 10 centimeter cube, which divided by 1000, so this is 0.010 decimeter cube of 0.1 mole per decimeter cube of HCl. This means if we multiply this two, we know how many moles of hydrochloric acid we are adding. So when we do this, we get 0.001 mole of HCl added. Now let's just go to the equation and see what happens. If you add this much HCl, you are going to remove the same amount of base, and you are going to add an added amount of MES acid on the other side. So after adding HCl, this is what happens. Moles of MES is going to be the original mole, which is 0.025, plus, minus, because we are removing, minus 0.001 moles. Because HCl is going to remove that much of your base to give you a new quantity or added quantity of MES acid. And when you do this, this becomes 0.024 moles of MES left or left over. Now if we go to MES acid, so moles of MES acid is simply 0.025, the original mole, plus the new moles of HCl, 0.001 mole HCl. So this happens to be 0.026 moles. We are almost there, except remember that Henderson-Hasselbalch has a concentration in it. So in order to find concentration, it's moles divided by volume, total. What is the total volume? The total volume is, you took 50 centimeter cube of buffer, you added 10 centimeter cube of HCl, so the total is 60 centimeter cube, or 0.060 decimeter cube. So now concentration of MES after HCl was added to it is equal to 0.024 divided by 0.060. When we do that, this becomes 0.04 mole decimeter cube. Concentration of MES acid complex is rather this many moles, 0.026, divided by the total volume, which happens to be 0.430 mole per decimeter cube. Now we are ready. We just plug it into Henderson-Hasselbalch. So the new pH is still same as pKa, plus log of, remember, base over acid. So it was 6.15, pKa doesn't change, plus log of concentration of the base is 0.4. Concentration of the acid is 0.430. So when we do this and plug it into the calculator, we get 6.11, which is a good example of, we added a little bit of hydrochloric acid to a weak base. Its pH is going to go down, but not by much, because it is a buffer. So it's maintaining its pH approximately in that neighborhood. It's a good example. You should work it out one more time yourself and see if you get 6.11. It's slightly messy, but I just wanted to do it on one screen.